Thank you very much. Thank you for the wonderful introduction. I'm absolutely delighted to be here. The introduction you have given me is absolutely correct in accordance with my website. And my professorship, I suppose, was in composite materials, and in particular the use of these full field non-contact measurement techniques. However, now that I've become professor, that has allowed me to explore other areas of naval architecture that inspired me to go and study naval architecture when I was 18. And that is, I always wanted to be a yacht designer. So this is kind of a link with my passion. The reason why I'm in the US is that I went to the Chesapeake Sailing Yacht Symposium, so I thought I'd keep the link going. But also, for any of you who have more recently or in the past visited Southampton as part of the exchange program, you will have done the basic naval architecture module in the first year. And I give this presentation in the second semester to our first year students doing basic naval architecture to show how I could link the research that I was really interested in doing with some of the hydrostatics and stability work that we've been doing within basic naval architecture. So this is a little bit of a crossover lecture. So I'm a child of the 1980s and 90s sailing yacht scene in Europe, and I have a very unhealthy obsession with the performance of sailing yachts from that era. And so my presentation today is a link between the rating that they were given at the time and their performance. A little bit of background. I started sailing on a quarter tonner back in the 1980s and 90s. With my parents. I was the young whippersnapper helmsman telling my parents finally what to do. And sailed on a boat called Mitzi, which was a weird design, came out of Japan. It was a Yamaha model, but it was based on Magician 5, which won the one-ton cup in 1978, albeit with a slightly different shape. I then went on to sail in the one-ton fleet offshore, and this is an Oyster 37, and I cut my teeth doing some of the big races around the Island Race and the Fastnet Race in the UK and in Ireland. I still sail now. I sail on the Solent. I used to sail on a Corby 25, and now I sail on a Mustang 30. So I still like to go out there and get wet. So my talk is about the IOR yachts, and in particular the one-ton class. So within the one-ton class of yachts, the yachts all got a rating in the same way that you do for ORC or IRC, and there was a limit on the maximum number that you could have. And in the IOR period, 27.5 pre-1984 was the number that made you a one-ton yacht. And designers would design specifically to that number. They would then be eligible to enter into the World Championships, which were held every year, with a chance, of course, winning. And they were all level rated, so they would all have the same time allowance, and so first across the line would win. There was no handicap. The designers were asked to design to the handicap. So in 1978, this was a small subsection of the fleet. So this was Ron Holland's Tilsag. This was Jim Young's Heatwave. This is Bruce Farr's Export Line. And this was Peter Norland's Stress. And as you can see just from those photographs, the shapes of the boats were very, very different. But they all measured exactly the same. So in theory, when the gun went off and they finished the race, they would all cross the line at the same time because the speed potential was identical. That's assuming that all of the crews, all of the tactical decisions, all of the wind shifts, all of the tidal stuff was all identical. Then in theory, these boats would all cross the finishing line at the same time. And of course, we know that for sailors amongst us, we know that those handicap systems are fundamentally flawed and that in strong conditions, some designs are better than in lighter conditions, upwind conditions versus downwind conditions. And I think we had plenty of talk about this at the symposium last week. So the rule that they were all designed to was an amalgamation of the Cruising Club of America and the Royal Ocean Racing Club rules, which were separate on either side of the Atlantic. They decided they would create a world rule, and they created the International Offshore Rule. It was written in Peter Johnston's book on handicapping that this was going to be the rule to last 1,000 years. Lasted about 30, and then it was done. So in order apologies, I'll just go back. In order to populate this equation, we are after this magic number R. And this magic number R is made up of a whole load of things. The most important one is MR, which is the measured rating. So after measuring everything on your boat, you would get this number R. And before, MR and R used to just equal each other. But as the designers started exploiting various loopholes in the rule, they had to build in some extra corrections. A movable appendage factor, because someone decided it would be a good idea to allow keels to move around inside their boat. A center of gravity factor to try and stop people stripping the boats out and making them into racing machines, which of course they did. And an engine propeller factor to stop people doing clever things with their engines or not having an engine on board at all. And so we have these factors that were built in, and the measured rating would give us R. Now, R is made up of the things that we know that drive the performance of sailing yachts. We have the length, we have the sail area, we have a draft correction and a freeboard correction, again, to catch the loopholists. We have the rated beam, and we have the rated depth. So we have these things that we know drive things. We know from just basic naval architecture, length to beam ratio is very good from a hydrodynamics perspective. So we know that these basic parameters that form the rule are also the basic parameters that we know drive the performance of a lot of our naval architecture craft. So in terms of the IOR measurement, they start off by taking the boat out of the water, and they start throwing a measuring tape on it. They first of all try and find a beam rating so that they can measure the beam. The beam is then going to allow them to determine where the forward and aft girth stations are going to be. So 2 lines here and 2 lines back here somewhere. And then that's going to end up allowing them to fix the measured length. And the positions then of the beams are then used to generate data that allows them to measure in different places to obtain the measured depth. And you can even see it even on this projection. It's always much better on the slides, but even on this projection, you can see that just at this location here, there's a bump in the hull. And that's bumped particularly in the place where the beam is going to be, because it's trying to make the rule think that the boat is wider than it actually really is. And so if you have a boat that's a certain amount long and wider than it thinks it is, even from our basic knowledge and understanding of basic naval architecture, that low value of length to beam ratio is going to be hydrodynamically less efficient than the long, slender vessel. But it's a cheat, and this is what the rules, the designers were doing. They would do all sorts of funny things, making flat-bottomed U-shaped sections at the bow. They would pinch in the stern here at the measurement station to try and reduce the measured length. And this is Stephen Jones designed SJ36, and you can see how tortured it looks. It's got this massive bustle here, looks like a 12 meter. It's got this big dip in the shear line here where the measurement for the aft girth station is going to be. It's got this really flat area here and this kind of bulge here. And this was Stephen Jones. He was very famous for creating really bulgy looking sailing boats. And it was these kinds of measurements that resulted in a lot of armchair naval architects sitting around in their yacht clubs going, oh, the IOR rule creates nothing but really bad sailing boats. They only ever go slower. All the designers are designing their boats to go as slow as possible so they can win races. So this was the commentary that was coming out. And growing up with this commentary and having a background in naval architecture, I wanted to answer the question, is this really true? Did the boats really get slower to win races? Which is what they were saying. So I set out on wanting to do this. Oh yes, there's an extra picture in here. I took this picture only the other week. I was on the Isle of Wight, and I was visiting an old wooden boat building museum that's on the Isle of Wight. And sitting in the middle of a yard was this boat on a trailer that I'd never seen before. And sure enough, look, it's got a great big bump in it, just about there. So straight away onto Facebook, because I'm old, onto Facebook and put out a post, I spy with my little eye something beginning with I, and everyone of my age went IOR, because that's what that bump essentially resembles. It's an indication of this boat having been designed in the IOR era. So the bumping continued right through until the 1990s. This is Andelsbanken, which was an ex-yacht, which you can just about see in the projection. An underwater bulge, again, trying to take advantage of some depth measurements, cheat. And so this continued throughout the entirety of the IOR period. And the question was, were the boats fast or slow? So in about 1984, I think, shortly after, 1974, Rob Humphreys, a reasonably well-known yacht designer in the UK, wrote an article for Seahorse magazine that plotted the sail area against length, the length against displacement, which obviously then led to a sail area versus displacement axis, and plotted boats from all around the 1970s and early 1970s onto this chart, with the idea that large sail area, large displacement up here, small sail area, large displacement down here. That's our cruising boats, not really relevant here for the racing scene. Long, low displacement, small sail area, and then our small displacement, long and large sail area up here. And you can see that these form kind of bands across this diagram. And the desire is to kind of move in this direction. So in his article, Rob Humphreys wrote a few things. Golden Apple, which is there, and Chartreuse, which is there, have lots of sail for their length and are known to be potent in the light to moderate. Chartreuse with a little more length should be faster downhill in a blow. Quite subjective sentence, should be. You know, it was a kind of a guess, but a guess based on experience. Lightning, evident is over here, a bit heavier, tends to indicate that she needs a bit of breeze to get her going. Wording and phrasing is a quote-unquote from the 1970s. However, her downwill capability appears to suffer because of a fairly poor sail area to displacement ratio. Again, quite subjective. And high tension, which is this dot here, quite well placed in terms of displacement to length area, but her lower length to sail possibly explains why she is at her best in a breeze uphill and down. Again, quite subjective in nature. And I wanted to turn that subjective comment into some scientific fact, I suppose. In 1974-75, the thought of doing velocity predictions of sailing boats was a pipe dream, except for a few people working at MIT on the Pratt project. And I was really lucky. I was rooting through Ron Holland's archives one rainy day. Ron Holland's office is based in the town that I grew up in. I came across this piece of paper, and I was quite young then. I didn't realize what it was, and I put it away. And it was later on I realized that this is actually the output from one of the printouts from the running of the Pratt VPP for a boat called Silver Apple. So I asked Ron and his colleague Rob Doyle, who now runs his office, I said, you don't happen to have the lines of Silver Apple, do you? And he said, yeah, they're in that cupboard over there. So I managed to get a copy of them, and that started my whole project. So you may or may not know that the VPP is essentially a balance of forces. We have the aerodynamic forces pushing on the sails, and we have the hydrodynamic forces of the water pushing on the underwater part. And when we balance all of these out, we get three important things from a velocity prediction point of view for these displacement type sailing boats. When the righting moment matches the heeling moment, we get constant heel angle. When the aerodynamic thrust matches the hydrodynamic resistance, we get constant velocity. And when we get our side force match, aerodynamic side force and our hydrodynamic side force matching, we get a constant leeway angle, which allows us to see how much rudder we need to produce to sail in a straight line. And when these three things are balanced, we have this balance of forces. And this would be, for a given set of sails or a given shape of the underwater body, would result in some kind of speed. And that's what we're after, velocity made good, velocity in the right direction. So in order to be able to do this, we need both the aerodynamic data and the hydrodynamic data. Oh, blatant plug. If you want to read a little bit more about this, Professor Molland, Professor Turnock and Professor Hudson, all from University of Southampton, wrote a lovely book called Ship Resistance and Propulsion. And in there is a propulsion bit, which is the sails for sailing boats. There's a hydrodynamic bit for sailing boats under the hydrodynamic chapters. And then there's a solution, a worked solution for a VPP in the back in chapter 16 or chapter 17. Sorry for the plug. But also we have available to us velocity prediction programs that are out there, and I use the one that's local to us. Our consultancy arm, the Wolfson unit, produced one called Wind Design 4. There's also one contained within MacSurf. They do things slightly differently, but they're much of a muchness. I used Wind Design 4. But for it, you need both the aerodynamic data and the hydrodynamic data. So the aerodynamic data comes from the IOR certificate, and because the IOR certificate has the measurements of the sails on it. And empirical data is used to develop the forces. So here's a copy of Silver Apple's certificate, and you can see our IJPE and BAD and all sorts of other measurements and spinnaker measurements, etc. So we were able to get all of those measurements from the IOR certificate, and then use the ORC's VPP documentation in order to generate the forces generated by the sails. So this would allow us to have all of the aerodynamic forces, aerodynamic thrust, aerodynamic side force, and the resultant heeling moment. The hydrodynamic forces, well, the righting moment came from the IOR certificate because they did an inclining experiment on the boat as part of the measurement to determine the vertical center of gravity. So that was great. So I had a VCG value for the boat. So there's the little bit on the certificate where you have the movements, and we have a pendulum length. So PL there is our pendulum length, and then the measurements that the pendulums had swung. So we have all the ingredients that we know from doing a little inclining experiment that we can get our vertical center of gravity from. And then in addition to that, I used a publication from Delft, which was entitled Approximating the Hydrodynamic Forces on a Sailing Boat, based on the Delft Systematic Yacht Hull series. So here we're getting all of our regression. We're going to use some regression equations in order to get our hydrodynamic forces. But in order to do this, I needed the hull. And so in order to calculate this, I need the hull. If I need the hull, I need the lines plan. I need to be able to generate some hydrostatic particulars. In the 1970s, the lines plans all came as sketches. And so I had to convert those sketches into a computer model in order to be able to do the hydrostatics and stability, the hydrostatic calculations. And for those who were in Webb last semester, we used exactly the same methodology, sketching our own sketches on a piece of paper and putting them into MaxSurf so that we could create our hull geometries that we dream up in our heads and turn them into 3D CAD models. I used exactly the same methodology that I teach to the students in my basic naval architecture module. This allowed me to get a MaxSurf model, and the MaxSurf model then allowed me to run the hydrostatics and stability calculator, which gave me all the hydrostatics I needed to populate the regression equations. So now I have everything I need to do the resistance part, the hydrodynamic forces. So what do we have? We have a whole load of equations that come from that Delft paper. We have viscous hull resistance. We have viscous keel resistance and viscous rudder resistance. We have our residuary resistance, that's our wave-making resistance of the hull. We have our residuary resistance of the keel. We have the added resistance of the hull due to heel. And we have the added resistance of the keel due to heel. And we have induced resistance due to leeway. And when you look at all of these equations, they're populated entirely by the things we know from basic hydrostatics, from my basic naval architecture module. Length, draft, there's beam, there is area of the waterplane, length of the waterline, the position of the LCB, the position of the LCF, prismatic coefficient. There's a few others up there as well, that's LCB squared. So all of these are just hydrostatic particulars that we can produce out of our design software. So with the model and these equations, I was now able to get all of the hydrostatic data, all of the resistance data. The key one here is the residuary resistance. We have lots of other methods for calculating a lot of the other things, but the one that's really important that comes out of the work by Delft was this residuary resistance equation, and it has these additional constants, A1, A2, A3, A4, A5, A6, A7, and A8. And they come from a table, and the table is the constants against Froude number. So knowing what speed we're doing allows you to interpolate in order to get those numbers to put into the equation. And so we have now everything we need. We have a speed, we have all the equations for the hydrodynamics, I have the dimensions of all of the sail stuff from the IOR certificate to get all of the aerodynamics. So now I can put all of this information into the VPP and do the force balance. And we have our non-dimensional Froude number, yes, which you all know. And also, we can rearrange our Froude number to give us a hull speed. This is kind of a maximum theoretical speed that a boat could move along. And the great thing about this hull speed is that it works really for the IOR boats because they never plane. They just create great big holes in the water that you have to push aside. So they always travel at a maximum of hull speed, which gives me a good idea as to whether or not the VPP is over-predicting the results. We also have a hydrodynamic side force that we need, and this comes from a lift curve slope measurement, which is a side force, hydrodynamic side force, squared on one axis and resistance, total resistance on the y-axis. And it's made up of some from measured data, and you can plot some lines through it. So that once you know what your total resistance is, you can come across and then work out what your side force is. And it comes from an equation that looks like that from the Delft magazine as well, Delft paper as well. So now we're balancing our forces in our 3 degrees of freedom. So total resistance giving us boat speed, hydrodynamic side forces and aerodynamic side forces to give us leeway angle, and the righting moment and heeling moment to create heel angle. And the way it works is you start with a guess, you choose a true wind speed angle and a true wind speed and a guess for the boat speed. Plug everything into all of the equations, look at how they balance or don't balance, and adjust the speed until they all balance. So you're just solving for speed, and it's an iterative process. and then all the equations will be satisfied, and then you have the speed that the boat is doing in those two conditions, and given the shape of the hull. And you get a nice polar diagram now, so you can see that in 4 knots of wind, this is what your speed potential looks like for a variety of different wind angles as we go around the outside. And as you'd expect, going downwind, you go a little bit quicker, and as the wind speed increases, you go a little bit quicker again. So it all kinds of makes some sense. And the hull speed was such that I think the hull speed for these boats is around 9 knots. That's about as fast as they could possibly go. And we get about 9 knots in 20 knots of breeze downwind. So these boats are slow, but they're accurately slow, or what I believe to be accurately slow. So I created my own VPP, and you can create your own VPP. You just follow the equations that are in the textbook, and you can result in being able to predict the performance of your sailing boat. Now the problem is that some of you might have slightly more exotic sailing boats than the IOR. And here then we have to think about something slightly different. So if any of you were attending the Chesapeake conference last week, you will have seen the presentation I gave on my PhD students' work. And this is a little snippet into how much more complicated it can become once we start getting even more high performance. So predicting how quickly a basic car from Ford goes versus how quick does a Formula One car or an Indy car going to go. And these are the high performance sailing boats that we're talking about. So these are the America's Cup boats. They're AC-75s. They sit on hydrofoils. They do 3 times or more the boat speed than the wind speed that's blowing. So in my example of my VPP, 20 knots of breeze downwind doing 9 knots. Yep, they're really slow. In 9 knots of breeze or 11 knots of breeze, these boats will do 30. So these are incredible machines. They're incredibly efficient aerodynamically, and they're super cool hydrodynamically. And what my PhD student has been doing is looking at the hydrodynamics. So the boat is set up in exactly the same way, and the set of force balances now has to include some additional things. So we still have aerodynamic side force and hydrodynamic side force. We still have righting moment and heeling moment. And we still have aerodynamic drive force and hydrodynamic resistance. There's still the 3 forces and moments that we're dealing with from my VPP. But now we have vertical force and gravity. They have to be balanced to sit perfectly on the hydrofoil. We also have pitching moments. So this is like an aerodynamic pitching moment and a hydrodynamic pitching moment. They are going to have to balance with each other. And then we have the yaw moments as well. So all 6 degrees of freedom come into play. And this then becomes a much more complex problem to solve. Of course, hydrodynamically, we now only have this in the water and a little bit of this. So hydrodynamic resistance goes through the floor. Aerodynamic thrust is very efficient. And so these things can go really, really quickly. The foils have to be designed within a box, so they dictate the shape that they can be. And the force models become really complex. The sails are providing drive force. They're also resulting in side force, heeling moment, pitching moment, and yawing moments. So because we've now brought into play all of the degrees of freedom, the 6 degrees of freedom that we normally consider for a marine craft. The hull producing aerodynamic drag now as well. We're going 3 times the speed of the wind. Aerodynamic of the hull now becomes really important. So it's not just the forces being generated for thrust, but also the negative forces being generated by the fact that you're moving really quickly through air. Side force, gravitational forces, and all of the three moments. The crew produces down force, a weight downwards, righting moment and pitching moment. The rudder and elevator producing drag, side force, sometimes positive vertical lift, sometimes negative vertical lift, and the associated moments. The leeward foil is canted, the windward foil comes out of the water and results in a righting moment. So there's so much complexity going on. And before the first edition of the America's Cup, Dan Bernasconi did his PhD at Southampton, chief designer of Emirates Team New Zealand, said it may well be the area which decides the next America's Cup, and he was referring to the hydrofoils. So a sophisticated hydrofoil design and optimization technique is needed. And this is the work that my PhD student Raphael is doing alongside Professor Turnock at the University of Southampton. Karsten works at DNVGL and worked for America's Cup teams in the past and wrote the 6 Degree of Freedom VPP. And Professor Walter from Berlin is involved in doing very complex and very cool optimization techniques. So there we go. So that's kind of the end of my talk. The paper is by my PhD student, most recently one published in the Chesapeake Sailing Yacht Symposium, as well as the Auckland conference, sister conference that was held last summer, and InnovSail, which is held in Europe in the year before that. So every third year, Chesapeake comes along, and likewise for the other two. They're freely available to download on the internet if you're really interested, and I'm willing to take questions.